Hi there, Year 11. Today we're going to look at rational functions. So some of these rational functions we've probably already seen a little bit before, but we're looking at this in a little bit more detail now. So rational functions are related to rational numbers. So you may have remembered some rational numbers. Can you think of what do we mean by a rational number? The word rational comes from the word ratio. So a rational number is any number that can be written as a ratio of two integers. So in other words, any fraction, half, 23 over 74, any of those are rational numbers. That means, of course, any decimal, right, 2.5, any decimal can be written as a rational number. So rational functions are those where we have a fraction of two functions, not just a fraction of two numbers. So a rational function involves algebraic fractions, and you would have dealt with those in Year 10. All these functions have a vertical asymptote. We've already started looking at those when we were doing domain and range. These are current values for x, which are excluded from the function's domain because your denominator cannot equal 0. So by now you should have the habit of looking at the denominator of a rational function to see where doesn't it exist. Up to now you've probably mostly been looking at your calculator, graphing it and then looking, but you should also be starting to get the habit to look here at any function involving x on the denominator that cannot equal 0. So here we've got two functions, but this one cannot equal 0. A particular type is what we call a reciprocal function. So reciprocal 1 over. So here's our reciprocal because our x is in the denominator, and up the top we have a constant. Obviously we don't want anything, we know that x cannot equal 0 for this one, but k, there are certain values that k could be, almost anything except 0. It would not make any sense to have k equal to 0 because we don't have a function. So that's the limit to the values for that parameter. So x is our variable, k is what we call a parameter. So in this example, we're going to look a bit closer at this, though you would have looked at these in the domain and range. F of x over 1 on x. We want to see what happens to the function as x approaches certain values. And the notation we're going to use here is that arrow, meaning approaches. So this function is undefined at x equals 0. All right, we know that because our denominator cannot be 0. So that gives us, from our graph, our vertical asymptote here. You may already have recognised as 1 over x as our hyperbola, a rectangular hyperbola, because it takes those two opposite quadrants. As x approaches 0 from the right-hand side, and the way we say that is it's coming from the positive direction. If it's coming in from the right, it's coming from the positive end. As it approaches 0, then what does our function approach? We can see our function's getting bigger and bigger and bigger. It approaches infinity. So our f of x approaches infinity as x approaches 0 from above. As x approaches 0 from the left, what's happening? Our function's getting smaller and smaller, more and more negative. So the value of the function is approaching negative infinity. So if we're coming in from the positive, we use that little positive sign up here above the 0. If we're coming in from the negative end, we use the negative little sign above the 0. You may also notice that this function is symmetrical. Remember, something is symmetrical if you could like fold it in half on top of each other. So here we've got, this can be symmetrical around the two lines that I've drawn in so far, where we've got y equal to x, so that line there. Y equals X is a line of symmetry. I was trying to get yellow, but it wasn't being nice for me. All right. Another line of symmetry is this other line here. Y equals minus X. So in other words, on Y equals X, you could fold it in half and it'd be on top of itself. If you used Y equals minus X, it would fold over on top of each other. So two lines of symmetry around Y equals X and Y equals minus X. It also has a horizontal asymptote at Y equals 0. So that's this line here. We've got some more colours here. All right, so this line here is a horizontal asymptote, and we can see that because it approaches but never touches the x-axis. It approaches but never touches or cuts the x-axis. So let's look at our limit statements for that one. As x approaches infinity from above, so if x is approaching infinity from above, that means it's going this way, but it's above the line. What happens to our value of the function? It's getting smaller and smaller. So and x approaches infinity, f of x approaches 0, and it's coming from above. So you could put the little plus sign there again. As x approaches negative infinity, so as x is going in that direction, then our function is going on further to approach 0 again, but from below. So it approaches that line of y equals 0, but never touches it. So that means it's a horizontal asymptote. So in the general case, what if we've got our constant is not 0, but we have a different value for k? We can see, this is on your textbook, so you can open this up and look at it yourself. There's our y equals x, and we can plot that, and we get the hyperbola we just talked about. What if we plotted y equals 2x? What do you think is going to happen now if we have 2 over x? You could pause that and try and sketch in what you think it would look like. So if you have a go at that, hopefully you've thought it's the same as 1 over x but times 2, which means all our y values are just being multiplied by 2. So they should all be bigger. So let's plot that and have a look. There it is. So this value here is now twice as big. So it goes up to 2. This is twice as big up to here. So it's further away from the asymptotes. What if we now wanted to plot y equals 4 over x? You probably guessed it's going to be even further up. So 1 here now goes all the way up to 4. It's going 4 times that to get to this value. What happens if we plot 1 minus 1 over x? So that means get the graph of 1 on x, which is our blue one here, this line here. Now, get the y value, now multiply it by minus 1. So plus 1 now comes down to minus 1. This value comes down here. So it's sending it down below the axis. If it's positive, it becomes negative. If it's a negative value, it will become positive. Let's check, and hopefully we're right. Oh, phew. There it is. All right, so we now have it flipped across the x-axis. And then obviously if we now go minus 2 over x, it'll be like the 2 on x graph, but down, will be flipped across your y-axis. So this point here is now down here. So what we'd expect you now to be is very familiar with this hyperbolic function, the reciprocal function. Let me shut that down so we can do a bit of a summary. You could copy those graphs into your file, and let's do a summary. I might go back and put that summary in a moment. So when k is greater than 0, see if you could pause it and fill it in yourself and then check your answer. So the larger the k value, the further away from the x and y axes. We'll talk more about this in chapter 5. If k is less than 0, then the graph is reflected across the x-axis. Now let's look at something a little bit more complicated. So these rational functions are not just 1 on x, but we've got a binomial on top and on the bottom, in the numerator and the denominator. Again, you will remember from the domain and range section that you look at your denominator to find where that equals 0, then x is equal to 1. That's going to be the equation of our vertical asymptote. All right, you always write the equation as x equal to 1, but our domain for this is written as x such that x does not equal 1. This is how we calculate to get our asymptote. So look at the denominator to determine the vertical asymptote. So we've done that one. Let me move this over because I'm covering over a few. There we go. All right. Okay, so we've got our vertical asymptote at x equal to 1. Done that. Note the function changes sign on opposite sides of the asymptote. So here we're at positive infinity. Now down here we're at negative infinity. Over here we're at positive above the asymptote. This one will end up going down. This side will end up going into the negative region. All right, find the x-intercepts. How do you find the x-intercepts? If you think you know how, then this is a good place to pause and calculate it. So your x-intercepts is where your denominator equals 0. Not your denominator, your numerator equals 0. So we want to solve 2x plus 1 equals 0, x equals minus a half. So there's our x-intercept at minus a half. To find the horizontal asymptote, we need to consider what happens as x approaches positive infinity or negative infinity. So when x approaches positive infinity, we can look at our equation up at the beginning here. Let me just pull this down a little bit further. All right, so when x approaches positive infinity, and if we look at our equation, if we've got these, in the numerator it says we're going to go 2x plus 1, our plus 1 really isn't making a big difference, just as our minus 1 in the denominator doesn't make a big difference. So they become insignificant as x approaches infinity. So our function really is going to be impacted by this part only, the 2x plus it over x. So that gives us our answer of 2. So we find that the horizontal asymptote happens at y equals 2. And that's at this point, where we're here, we're low values of x, it is a big difference. But as x approaches infinity, or negative infinity, that difference becomes so small that it becomes insignificant. So we can say or work out that our horizontal asymptote is at y equals 2. All right? So one of the ways we can either work out the horizontal asymptote, we can either just look at these values here and ignore the others. Another way you'll often see it written is in this form, where here is our horizontal asymptote, because this part of the function, this whole part of the function approaches 0. So as x approaches infinity, this part approaches 0. So how do we get it into this form when we're starting over here? So the strategy for this is we want to get the 2 on its own. So you start off, it's a bit like computing the square. You go 2 and then make the same as the denominator up at the top. So we're going to eventually separate this so we can cancel it. But if we've gone 2x minus 1, that's the same as 2x minus 2, we already had a plus 1 from up here. So that's our plus 1. We now need to undo what we just added. We just added this part. So we've now got to, this is the same as 2 times minus 1. So we want to now go plus 2 to undo that. So we can't change the equation. So our equation now looks like 2x minus 1 plus 3 over x minus 1. We can now separate that into 2 fractions. 2x minus 1 over x minus 1 plus 3 over x minus 1. And you can see that we can now cancel this, because that's the same in the numerator and denominator. So this is written as 2 plus 3 over x minus 1. So it's the same equation, just written differently. So therefore, as x approaches infinity, 3 over x minus 1, I'll write that again. 3 over x minus 1 approaches 0. Therefore, our function y approaches 2. So our horizontal asymptote is y equals 2. All right, when we get to class, I want us to be able to consider these questions. So we'll stop there for today. Thanks, and look forward to seeing you in class.